All right, so I'm going to present on video capsule networks. So capsule networks, as we've seen, they achieve very good results in classifying small images, so like data sets like MNIST and small orb. But they've rarely been successfully applied on high dimensional data like large images and videos. The reason for this is that the capsule routing procedure is computationally costly and deeper networks can't fit into memory. I'll briefly explain the computational cost of capsule routing. So if you think of convolutional capsule routing between two layers, you have CL represents the number of capsule types in the layer L, and CL plus 1 is the number of capsule types in the second layer, and KT, KX, and KY is the receptive field of the second layer capsules. So for each capsule in the second layer, it has to calculate this many votes, right? And each vote, it could be a 16-dimensional vector. So if you compute that at each pixel, the number of votes becomes very large, and it's very difficult to fit these into memory. So the number of votes becomes large if either the size of the layer is large, so if you have a large video input with a great number of pixels, or if the receptive field is large. I'll show this visually now. So first I'll go over conventional convolution and compare that to convolutional capsule layers. So given an input layer, we have some time dimension, some height, and some width, right, for videos, and we have some number of channels. We have a receptive field that is scanned across the image, and we apply some set of kernels. We do element-wise multiplication and then summation to get some scalar activations, and those are placed at that position in the output layer. This is conventional convolutions. Convolutional capsule layers are similar. So we have an input layer, but instead of different channels, we have different capsules. So we have CL capsule types. And each capsule is represented by a 16-dimensional pose matrix and an activation. Then we have a receptive field, once again, but instead of kernels, we have transformation matrices. So these transformation matrices try to get the lower level capsules' prediction of the higher level capsules. These are multiplied by these lower level capsules to get our votes, and these votes are passed through a routing algorithm, in this case the EM routing algorithm, to get our output capsules, and those are placed in the output layer. So as you can see, this number of votes, since each one of these votes is a matrix, this number of votes is quite large, and if you try to fit a deep network, capsule network into a GPU, you probably won't be able to. So we introduced two simplifications to this convolutional capsule routing. So the first is using the same transformation matrix for different capsules of the same type, and then capsule pooling. So if we go back to this figure, we can, instead of having a transformation matrix for each position of the receptive field, we can share transformation matrices between capsules of the same capsule type. Then we can multiply these transformation matrices with the receptive field and get our votes in that manner. But this doesn't really solve our issue because we still have the same number of votes. So for that reason, we introduced capsule pooling. So once we get a receptive field of capsules, we can pool those capsules into a single capsule for each capsule type. So now, when we apply the transformation matrices, we multiply them and we get our set of votes. We reduce the number of votes we have. So now the number of votes is no longer proportional to the receptive field size. It's only proportional to the number of capsules you want in both layers. So this allows us to fit deeper networks into memory and allows capsule networks to work on higher dimensional data. So I'll now talk about video capsule networks, specifically on three different tasks. So the first is action detection, where we want to localize and classify humans doing actions in videos. The second is multi-modal task, where we want to segment an actor from a video based on some textual query. And the third is semi-supervised video object segmentation, where we have the first frame of the video segmented and we want to propagate that segmentation throughout the video. So I'll start with action detection. And this was VideoCapsuleNet. This was a NIPS 2018 paper. So modern action detection networks usually require multi-stage pipelines. So they have a region proposal network, and then those regions are passed through a secondary network that classify the regions and perform bounding box regressions. They often require optical flow, and they're rarely trained end-to-end. So ideally, we can create a capsule network that can propose that can localize and classify actions in a single end-to-end network. So that's what VideoCapsuleNet is. The input to VideoCapsuleNet is 8 frames of 112 by 112, so this is much larger than a simple 28 by 28 image. And the output is a localization map for each one of those 8 frames. So this is the overall architecture. I'll go over it briefly now. So it starts off with a set of 3D convolutions to obtain some feature maps. These feature maps have been downsampled to 28 by 28, but we still have the 8 frames. And then they're passed through a convolutional layer to get our first capsule layer with 32 capsule types. This first capsule layer is then followed by a convolutional capsule layer with that capsule routing to obtain 32 capsule types in Conv 2. Then these capsules are fully connected to a set of class capsules. So these capsules represent the actions within the video, right? So if our data set has 24 actions, we have 24 class capsules which represent the different actions in the video. And because it's fully connected, we're going to lose some spatial information. So for that reason, we have a coordinate addition, which I'll briefly go over in a couple of slides. So once we have those class capsules, we want to localize that specific action in the video. To do that, we mask out all capsules except the ground truth capsule and pass it through a fully connected layer and a series of transpose convolutions to get our localization map. Here, skip connections are used to maintain that spatial temporal information, which is lost by the time it reaches the class capsules. So now I'll go over coordinate addition. So suppose we have a capsule at this position at time step 1 and at height and width 4 and 2. That capsule is going to create some votes for the class capsules. And this is, let's say this is the example vote matrix. If we want to encode that positional information, we could do it quite simply by just adding in the coordinates in the final 3 positions of the vote matrix, right? So the time coordinate is added in at this position, then the height coordinate, and then the width coordinate. And then when routing is performed using these votes, the class capsule will maintain this spatial temporal information. So this actually helps improve classification and localization results quite a bit. The next thing is capsule masking, which I mentioned. So capsule masking is useful for regularizing the capsule network. During training time, basically all classes except the ground truth class are masked out, right, replaced by zeros. And during testing time, when we don't have the ground truth class, we use the predicted class, so the class with the highest activation, and we use that for the localization. So VideoCapsuleNet is trained end-to-end using 2 losses. The first is the classification loss. This is a margin loss. So basically what this tries to do is push the target activation, so the activation of the capsule corresponding to the ground truth class, to be higher than all other activations of the class capsules by some margin n. And then the segmentation loss is the standard binary cross-entropy loss. And then the total loss is just a weighted sum of both of these. The segmentation loss is down-weighted because it could dominate the classification loss. So we want to make those losses similar. So the VideoCapsuleNet achieves pretty good results on 3 different data sets, state-of-the-art results. So first is UCF Sports was the smallest data set we test on. It achieves 1% improvement in VMAP at 0.2 IOU threshold. For JHV, we see a larger improvement, so about 15% VMAP at this threshold. And then for UCF 101, which is the largest one we test on, we can see a much larger improvement, so about 20% for VMAP and about 2% for FMAP. So here's some qualitative results. So the red bounding box is the human annotated ground truth, and then the blue is the network's output. So as you can see, if there's multiple humans, right, it correctly segments the one doing the correct action. In this case, if the human moves off screen, it's able to segment it quite well. And in these last two, if there's quite a lot of motion, the network is still able to segment the human doing the action. So one thing you might want to know is how to interpret these class capsules. To do this, we ran some synthetic dataset experiments. So this dataset, we generate primitive shapes moving across a noisy background. And in this case, there will be 4 motion types. So there will be 4 class capsules, so linear motion, circular motion, some turn motion, and random motion. And these primitive shapes vary in different ways. So the shape, the color, the speed of these shapes would change throughout the video. So for example, these are 2 sample video clips. So a square moving to the right, and then a circle growing larger, right? These are 2 sample videos. So we can analyze the linear motion class capsule. We can give it different videos, but we change single properties of the video, so we could change the direction or the speed or the rotation and see how that changes the different dimensions of the class capsule. So these are the 16 dimensions of that class capsule, and this is varying the different, the direction of the motion. So 0 would be right, left to right, and then pi would be right to left, right? And we have basically every direction here. And we can see that the capsule dimensions change quite predictably as the direction of the motion changes. And then notably, if we look at the final 3 dimensions, these are the ones that correspond with the coordinate addition. So the coordinate that corresponds with the height changes most when there's vertical motion, and the dimension that corresponds with the width changes most when there's horizontal motion. So you can see that this class capsule, this coordinate addition helps the class capsule maintain this spatial information. So in summary, I've shown you a 3D, the generalization of capsule networks to 3D. I've shown you how capsule pooling can help fit deeper networks into memory. And I've shown you a capsule network that achieves state-of-the-art results on human action localization on 3 data sets. So now I'm going to move on to combining video and text in a capsule network using multimodal capsule routing. So as you saw in the survey earlier, capsules have been applied to several different modalities, images, videos, text, audio, 3D point clouds, but very little work has been done on merging these modalities. So one task in computer vision is actor-action segmentation from a sentence. So given a video, let's say this is our input video, and we want to segment an actor based on some textual query. So the dog is walking around the red cones, we would segment this dog here. And if we give it a different textual query, a woman in the green top standing on the left, we would segment this woman on the left. If we want to implement this in a capsule framework, you can create a set of capsules from the video and create a set of capsules from the text. And then you can use capsule routing to condition the video capsules based on the text capsules. And then you use these conditioned capsules to produce segmentations for all the frames in the video. Right, so here's a visual representation of that. So we have a video encoder, we get some video capsules, we do the same thing for the textual query, and then we pass that through some multimodal routing to get our routed capsules, and we get our output segmentation from these capsules. So if you're thinking of this in a capsule framework, both the video and the sentence will contain the same entity, right? So both the sentence and the video contain a woman, or both the video and the sentence contain a dog. So we can have a visual entity for the brown dog that's sitting, and we would have the same entities within the sentence. So sitting, brown, and dog. Right? The same thing with the walking white dog and the woman in the green top. So these entities are present both in the sentence and the video, so that should also be represented by the capsules. So given an input video, we get our set of capsules in a grid, and then the different entities within the video should be represented at those positions. So this woman would be represented by the capsules at the position of the woman, the dog would be represented by these capsules, and this dog would be represented by these capsules. Similarly, a sentence, if we create a sentence capsules, right, the different objects within the sentence would be represented in these capsules. So now we can use routing by agreement to find a similarity between these capsules and the capsules at these three positions. So we have those capsules at those visual positions, the sentence capsules, and then when we do routing by agreement, we would find when these are routed, there would be no agreement. When these are routed, there would be no agreement. But then when the same entities are present in both, we would find agreement. So the output of the routing would be capsules with high activations. So I'll go over briefly the algorithm. So we have our video capsules represented by their poses and activations, our sentence capsules, and our transformation matrices. So this is the algorithm. First, we get a set of sentence capsule votes. Then for each position on the grid, we get the video capsules votes at that position. We can concatenate the activations and votes, and then pass that through the EM routing algorithm. So that tries to find agreement between the sentence and the video at each position spatially within the video. So this is a visual representation of that. So we have video capsules in a grid, we have the sentence capsules, and we get our set of actor capsules by performing this multimodal EM routing. I'll now go over the architecture of the network used to do this task. First, the video encoder. So the input is 4 frames of 224 by 224 resolution. It's passed through an I3D network to get some feature maps, and then these feature maps are transformed into a 20 by 20 grid of capsules with 8 capsule types. The textual query is passed through an encoder. So first, the words are changed into 300-dimensional embeddings using word2vec. Then 1D convolutions are passed over those embeddings to obtain a single feature vector after max pooling. And then a fully connected layer is applied to get 8 sentence capsules. So once we have the sentence and video capsules, we perform multimodal EM routing using the algorithm I stated before. And this produces a set of actor capsules. For the data set we're working with, which is A to D, there's 7 actor classes and 1 background class. So we decide to use 8 capsule types in this for the actor capsules. This is not really necessary, but we find that adding this class to capsule correspondence really helps in the training of capsule networks. So similarly to the video capsule net, we use capsule masking, which lets us have this class-based segmentation. And that improves our results. So these masked capsules are then sent to an upsampling network. It consists of 5 convolutional transpose layers, and the output is segmentation for each frame that was given to the network. This network is trained end-to-end. It only really requires a segmentation loss, which is the binary cross-entropy loss. But if we add in a classification loss, that extra supervision helps the capsules learn more meaningful representations. And for that, we use the margin loss I mentioned earlier. And the final loss is a weighted sum of both of these losses. So we perform experiments in several data sets, but the largest of which was A to D. And it achieves state-of-the-art results across the board when compared to other methods. Notably, it performs much better at higher overlap thresholds, which means that the segmentations produced by the network are much better than standard convolutional networks. Here are some qualitative results. So given this video, we have 2 sentences. A person is walking backwards while being followed by a dog, and a black dog is crawling. So as you can see, The person and the dog are both segmented quite well, right? The gap between the person's legs is segmented, and then the dog's tail is finely segmented. So this is our network trained on segmentations. If we wanted to train it on bounding box annotations, we can see the second row here. So the segmentations are not as fine because it's trained on bounding boxes. But even with that those noisy annotations, our network is able to segment quite well. And here's another example with 3 actors. A baby and 2 dogs, and even when the actors are quite small, the capsule network is able to localize it quite well. And here's some video examples. So a parrot jumping, baby climbing up the stairs. So here's an example with 2 actors, the baby and the ball. And here's an example with the car bouncing and a person filming. So even when there's multiple people, it only selects the person filming. So you can see that the capsules are learning that representation of the sentences and corresponding it to the video. So I've shown you a new multimodal capsule routing method, an end-to-end capsule network for video segmentation from a sentence. And it achieves state-of-the-art results on A2D. So the final part I'll talk about now, the final capsule network I'll talk about is one for semi-supervised video object segmentation. So the task of semi-supervised video object segmentation is quite popular. So we're given the segmentation of the object of interest in the first frame, and we want to segment that same object throughout the video. So when there's multiple deer, we want to segment this deer of interest throughout the video. If we want to do this in a capsule framework, we can again think of capsules as modeling different entities within the inputs. And we could say routing by agreement, or routing finds agreement between these different entities. So if we leverage both of these ideas, we can use capsule networks for this task. So we, once again, create a set of capsules from the video. Then we create a set of frame capsules. The video capsules will model the different objects within the video, while the frame capsule will model the object of interest in the first frame. And then routing by agreement can find the agreement between these sets of capsules. So here we go. So we have our video, we encode it into some video capsules. We have our reference from in segmentation, we encode that into frame capsules, and then we pass that through some form of capsule routing to get a set of conditioned video capsules. So these video capsules should represent the object of interest within the entire video. So how do we do this capsule routing? One way would be to simply use the multimodal capsule routing I discussed earlier. That actually does achieve pretty good results, but more can be done applying attention into the routing. So if we can adjust the EM routing algorithm to find the agreement not only between all capsules that are passed in, but rather between 2 different sets of capsules, right? The video capsules and the frame capsules. And then this should condition the video capsules based on these frame capsules. So I'll go over that now, this attention routing. So we use the same terminology as the transformer networks and attention. So we have a set of value votes, key votes, and query votes. So the video capsules we multiply them by their transformation matrices to produce some value votes and some key votes, and the frame capsules are multiplied by their transformation matrices to get some query votes. So value, key, and query is common in the transformer network, and basically we try to find similarity between the query and the key and perform some sort of soft mask extension to get an output from the value. So first we get the query votes and we pass it through the EM routing algorithm to get a set of query capsules. Then we try to find the similarity between these query capsules and the key votes. To do that, it's a simple Euclidean distance between these. So we find the Euclidean distance between all the key votes and the query capsules to get our distance matrix. Then, so this distance matrix represents how similar the objects represented by these votes are to the objects represented by these capsules. So a small distance would mean that they're very similar, whereas a large distance means they're probably different objects. So then these, each row of the distance matrix is passed through a softmax. So the inverse of the distance is the softmax. So this gives us assignment coefficients, which tell our network how much of a lower level capsule from the video will send information to the higher level capsules. So we have our assignment coefficients. So once we have this, we can apply this to the capsule votes in the M step of the EM routing algorithm to get a set of conditioned video capsules. And these conditioned video capsules represent all the object of interest throughout the video. So I'll go over the algorithm now. We're given a set of video capsules, a set of frame capsules, and the different transformation matrices for the value, key, and query. So we get the different value votes, key votes, and query votes. We pass the query capsules, query votes into the EM routing algorithm to the query capsules. We compute the distances between the query and the key. We get the assignment coefficients through the softmax operation. And then we pass assignment coefficients and the value votes into the M step of the EM algorithm. So at the end, we would have capsules representing the object of interest throughout the video. So we use this attention routing algorithm in the CapsuleVOS architecture. So I'll go over the different parts of this architecture now. So the video encoder, the input consists of 8 frames at 128 by 224 resolution. These frames are passed through 6 2+1D convolutions to obtain some set of feature maps. And then video capsules are obtained using a convolution operation. And we end up with 12 video capsule types. The frame capsules, frame encoder consists, so its input is the first frame as well as the segmentation mask for the object of interest. No? Okay. This is passed through a series of 2D convolutions to get some feature maps, and then it's passed to a Conv LSTM. So this Conv LSTM helps the frame capsules remember objects when they leave the scene or they're occluded. And we end up with 8 frame capsule types. This is the video capsules and frame capsules are then sent through the attention routing algorithm to get a set of conditioned video capsules. It results in 16 capsule types, and it's a strided operation, so we get this dimension. Then these conditioned video capsules are sent through another capsule convolution. So both of these convolution operations make use of that capsule pooling. If not, this network would never fit into a standard GPU, a single GPU. So it's passed through a secondary convolutional capsule layer, and then these capsules are sent through a decoder network with transposed convolutions. And the output is a segmentation for those 8 frames of the video. So as you can see, the spatial dimension of these videos is not that large because we have to fit these into memory, and capsule networks are memory inefficient. So in order to deal with this, we introduce a zooming module. So what this does is, suppose there's a small object within a video. So as you can see, this person is quite far away. If you were to resize this to 128 by 256, the object would be maybe a couple of pixels large, right? It would be quite small, and then any network you pass that segmentation to will lose the object within a couple of frames. Instead of doing this, a zooming module is used to learn to crop a bounding box around the object of interest, so a higher resolution object is passed through the CapsuleVOS network. This allows for better segmentation for small objects. So this zooming module it helps for smaller objects. It's a 2D component with an LSTM layer, and the output is the bounding box dimensions centered around the object of interest. And these bounding boxes should encompass the object within the future 7 frames, which the network will segment. So CapsuleVOS is trained end-to-end. It uses 2 segmentation losses. So the first is a binary cross entropy, and the second is a dice loss. It makes the zooming module uses an L2 loss to find the height and the width of the bounding box it must produce. And it's trained end-to-end using the sum of these 3 losses. So this network is evaluated on the YouTube VOS dataset, which is a pretty recent dataset. It's the largest video object segmentation dataset that's available, and it achieves state-of-the-art results. And it's also almost twice as fast as other state-of-the-art methods. So here's a speed analysis of it. So basically, CapsuleVOS achieves 62%. S2S, sequence to sequence, achieves 2% better, but it's about 100 times slower because it uses online learning. So yeah. So here's some qualitative results. So as you can see, the capsule network is able to segment the objects quite well. So in this case, as you can see, even when there's quite a bit of camera motion, it's able to track and segment the object. Okay. And even when there's multiple objects, CapsuleVOS is able to segment the objects quite well and maintain the boundaries between the objects. So if you look at this example here, there's 5 sheep of interest, quite small, in a flock of sheep, and the network is still able to segment it quite well. Yeah. Here are some other examples. All right. So to see how CapsuleVOS deals with occlusion and objects leaving the scene, we could test the CapsuleVOS with and without the memory module. So as you can see, this parachute is segmented correctly, but then it leaves the scene and then it's unable to be segmented because the network forgets about the object of interest. But the use of the memory module changes this. So once the object leaves the scene, it's able to segment the object successfully. Similarly, in cases of occlusion, right, it's successfully segmented, and then this is occluded for quite a long time. But without the memory module, the object is lost. With the memory module, even after this large occlusion, the frame capsules remember where the object is, and it's able to successfully segment the bear. So here are some video examples. So the bear is occluded by this wood, and then also this woman segmented in pink is occluded by this other woman, and it's segmented even after the occlusion. So we can also see the effects of the zooming module. So for example, this is the first frame of the video. As you can see, the objects of interest, these 2 people and the ball, are extremely small. So we can test our network with and without the zooming module. So without the zooming module, the capsule network loses or missegments this ball after 20 frames, and then this woman and this ball are lost after 90 frames. But with the zooming module, the capsule network is able to finally segment all objects even after 90 frames. Similarly, with this example, without the zooming module, the segmentation deteriorates over time, and then by the 95th frame, it's completely gone. But with the zooming module, it's successfully segmented. So here are some video results. So as you can see, the spider is quite small, but even its legs are able to be segmented by the capsule network. And even these people who are far away can be successfully segmented. And so in summary, I've shown you the new attention routing algorithm and how it's used in a semi-supervised video object segmentation using capsule networks. And it achieves state-of-the-art results on the YouTube VOS dataset. So that's it. Yeah.